Hello, calc fans. How we doing this Monday morning? A little bit dreary outside, a little wet, a little chilly. Hope things are going well for you. Hope everything's going well at your house. Hope you're staying safe and your family is staying safe also. Please continue to practice your social distancing. Thank you for turning in your tests. I get them graded and get them posted. Solutions, or not solutions, but your grades posted because that'll be the last grade we have of this third 9 weeks. Today we're going to talk about Newton's method, and if I go too fast through this, feel free to hit pause. I will not be offended by that. Hit your pause button to slow me down a little bit because I'm trying to shorten my length of my YouTube videos that I send to you. So once again, here's your chance to shut me up. I'll be talking, you can stop me in mid-sentence and you can stop me, okay? So, today we're going to talk about Newton's method of solving equations. Okay, Newton's method of solving equations. Newton was one of the fathers of calculus. He also did a lot of stuff with physics, but he was also father of calculus. We have this equation, x cubed minus 7x plus 7. We want to be able to solve this. Well, in pre-calc, we looked at the idea of synthetic division, but the only thing we can come up with those is rational solutions. Probably not going to get rational solutions here. So Newton figured out another way using the idea of derivatives to be able to calculate a solution. First thing we want to do is in my y1, I want to type in this equation, x cubed minus 7x plus 7. So go, if you don't have your calculator, hit your pause button, go get your calculator, and come back and hit your go again, and we'll be good to go. So in your y1, we type that in. We want to find out what makes this equal to 0, which is, we've called these zeros, we've called these x-intercepts, we've called them roots. So we're looking at the idea of the x-intercept. So if I hit my graph button here, we see that we have quite a few values here. I'm going to zoom, I'm going to get my window to be a little bit smaller. So I can see it a little bit better. And you can see what we have here between the values of 1 and 2. The values of 1 and 2, we cross the x-intercept, which would be one of our values here. So what we're going to do is we're going to look for this value in here between 1 and 2. Okay, so how we can go about this by trial and error is by just looking at function values right now. So what I want you to do is I want you to calculate the function value. Calculate your function value at a value of 1. And go ahead and enter. Okay, and our y value is a value of 1. Okay, don't delete that out, we get a value of 1. Okay, that's not the value of 0 we want. So we need to be able to go somewhere in between these values here, or it's somewhere between 1 and 2. We tried the value of 1. We are above the x-axis, so it's obviously not equal to 0, and if I put 1 in here, I would get 1 minus 7 plus 7, I would get a value of 1. We want to get the equation to get equal value 0. But if I look, I'm a little bit closer on my x-axis this way to 1.5. So let's take the halfway point in between here and just type in 1.5. I don't have to go through the process of going back to value again. And I get a y value negative 0.125. So if we take a look at our graph, between the value of 1 and the value of 2, if I put in a value of 1, these are my x values, I'm up here at a value, y value of 1. if I put in a value of 1.5, I'm below my x-axis at negative 0.25. So if I'm above here and below here, I have to be somewhere, I have to cross the x-axis somewhere between those values. So, let's try the value of 1.4 and see if that works. So go ahead and plug in 1.4. Once again, you don't have to go through the process of it. What I get is a negative 0.056, which is closer. But I'm still below the graph or below the x-axis. I'm not quite equal to 0. So let's try 1.3. If we try 1.3, I get a value of 0.097, which is the key. That is a positive value. This was a negative value. So at 1.3, we are above the graph. So where we cross the x-axis is somewhere between 1.3 and 1.4. Well, let's try halfway between them, 1.35. So if we put in the value of 1.35, we get a negative or a positive 0.0103. This is a positive value, which means I'm still above the x-axis. So the question I ask you is, are we going to be in between 1.35 and 1.4 or 1.35 and 1.3? Well, since both of these are positive, both of those values are above the x-axis. Since this one is positive and this one's negative, I have to be somewhere in between 1.35 and 1.4. So let's just go ahead and try to find another value. You pick any number that you want. Let's go 1.37. Let's see what happens at 1.37. 1.37, I get a negative 0.018. So, between 1.4 and 1.37, I'm negative on both of them. But between 1.35 and 1.37, I got one positive, one negative. So I have to be somewhere in between. So let's go one other value. Let's go our function value at 1.36. 1.36. We get negative 0.0045. The key is that we are negative. So that means that we have to be somewhere in between this value here and this value over here. Well, what's the halfway point between those two values? Let's just go for giggles, one other value, a function value at 1.355, because this would be 50, this would be 60, let's go 55. Let's see where we're at. 1.3, 1.355. And we see we get a 0.0028. The key that this is a positive value. So this one's positive, 0.350 is positive, and 0.360 is a negative. So we have to be somewhere in between the 1.355 and 1.360. One thing about 55 and 60. So we can continue this process until we get closer and closer to a zero value if we wanted to. Okay, and it is a painstaking process, but we can do it. If you want to try the value 1.357. Okay, and we can continue to narrow this down. It's going to be an irrational number. Never terminate, never repeat. We'll always be able to get closer and closer and closer to it, but your calculator will eventually get it to zero, but that's just because of decimal places and rounding. What Newton figured out was a way of being able to go through this process to be able to calculate these zero values, or these values that make this function equal to 0. And that is Newton's method. And this is a guess and check for solutions. Okay? We guessed and we checked, and we continue to guess and we continue to check for solutions. Okay, that's a painstaking process and very time-consuming process. So let's take a look away what Sir Fig of Isaac Newton said and how we could be able to solve this equation. He told us, and he derived this. Xn plus 1 is equal to xn, the function value at xn, and then this is divided by our derivative at xn. Now, what this n value is, and once again, if I'm going too fast, I won't be offended, hit your pause button. Okay, what this n value is just a counter number. N is equal to 1, 2, 3, 4, 5, 6, and so on. X1 would be your first guess. And in each one of these, you're going to have an initial guess. And what you need to be able to do is signify what your initial guess is. Now, how you come up with your initial guess is, I would look at a calculator. I get the function in the calculator, clickety-clack, clickety-clack. What's a value, what's a whole number that I'm close to? And go from there. So if I take a look at what this looks like, in my initial guess, this means n is equal to 1. Your initial guess, that means n is equal to 1. So if I take a look what happens here, I have x1 plus 1 is equal to x1 minus f at x1, or f prime at x1. So this would be x1 plus 1, which is x2. So your second guess value, and what we will do is we'll continue to come up with predictions here. Your second guess value comes from your first guess value. We have our first value, our x1, our function value at x1 divided by our derivative of x1. And that's what this signifies here. Maybe. Sub in x1 and solve for the next value, x, that will be closer to the root of the equation, which is x2. You sub in n equals 2, it solves for the next value of x, that will be closer to the root of the equation, that would be x3. And that's what I signified up here. So you just continue to put in another n value, put in another n value, put in that other next n value, then you will get your next guess value. If x1 is equal to 1, let's find x2. Once again, if I'm going too fast, pause it. Well, my function value, or my function, is once again x cubed minus 7x plus 7. Okay, that's my function. X cubed minus 7x plus 7. What we are also going to need is we're going to need to know our derivative. So our derivative of our function, go ahead and take the derivative of it. We have 3x squared minus 7. That's our derivative. We need these two values here. We need these two functions here. So what we're going to do is we're going to calculate. We're going to use an x1, our first initial guess, to be the value of 1. So to find x2, this is n equal to 1, we have to take x1 minus our function value at x1 divided by the derivative at x1. which would be x1 is the value of 1, minus our function value of 1 over the derivative at 1. Now this is easy to do right now because we got a whole number. What I would suggest you may want to do is into your y2, so you can calculate a value of your y2. Into your y2, type in your derivative, which is 3x squared. 3x squared minus 7. Type that into your y2. So then you can now utilize the derivative. But what you're going to see is this is going to be very cumbersome, just like it was up top. We could do the first value here. We have 1 minus our function value at 1, where our function value at 1 would be a value of 1. And our derivative at the value of 1 would be 3 times 1 minus 7, so we have a negative 4. So we have 1 minus a negative 4, so this would be 1.25. This is your x2. Well, to find our x3, that means n is equal to 2. Our x3, this would be x2 minus our function value at x2 over our derivative at x2. So we have 1.25 minus our function value at 1.25 over our derivative at 1.25. Okay, now it starts to become a little bit more taxing because now I have to find two different values and it's not going to be as pretty as it was before. And we'll take a look at how we can make life a little bit easier for ourselves. So if I wanted to, I could go and calculate value. Gives me both my functions now. 1.25. Okay, this is my first function, 0.203125, 0.203125. That's going to be on top. Then my calculator, if I hit my right arrow, maybe, value 1.25 gives me my first one. Hit my bottom arrow, it jumps me to, if I hit my down arrow, it takes me to my second function. So I have negative 2.3125. Once again, this becomes a little bit cumbersome because of the numbers. So if I would do this calculation, once again, watch your negatives. 1.25 minus 0.30125 divided by negative 2.3125. I get 1.38027 and a bunch of change. Well, problem is trying to carry all these decimal places out, it's going to be difficult for us. So how can we make life a little bit easier on ourselves? There's going to be a KYC exercise at this point. Know your calculator. Let's take a look at what we can do with your calculator. I have y1 is my function and y2 is my derivative. What your calculator will allow us to do is if I go back to my screen, I want to clear that out, that's fine. Let's type in x minus. Now, we want to subtract off that fraction. What your calculator will allow us to do. Hit your vars button. Hit your vars button here. Hit your right arrow for your y variables. And get your function. y1 parenthesis of x. Divided by vars, y vars, function, y2, parenthesis, x, and parenthesis. What I've just typed in is what I've been dealing with here. My Newton equation. I have x, my function value at x, over y2, my derivative at x. Now if you hit enter, you get some funky stuff there. Now what your calculator will do for you, and this is so nice, you guys get it so nice with your calculator. Take this X button up here, and it's hit the button over here, it says store. I screwed that up. Let's take the value of 1, and then store this to X. What this will do for you is wherever this calculator sees an X variable, it will use the value of 1. And hit enter. And what it does, it pops up there. Now, what I want to be able to do is I want to be able to pop this function back in and utilize it again. So let's go second and entry. I don't want that one. Second and entry. That's what I want. So I have this function. Now what's going to happen is this value of 1 is going to get ran through this function. And I get the value of 1.25. Now, this is where your calculator comes in nice for you. Got a nice orange face for you. This calculator, if you look like a pumpkin. What we can now do is we can hit our store button and then store this answer to X. Let's store this answer to X. And let's hit enter. Okay, now all my X values is 1.25. So I go second and entry. I don't want that one, but I want this one. I pull it back down again. I now get my 1.33, which I was getting over there and I didn't get it correctly. 1.3378. And you want to write all these decimal values out because we're going to look to see the point where it starts to repeat itself. So go ahead and write this value down. And now this is going to be my next value that I'm going to use to guess. So I'm going to store this to X. Second entry, pulls my equation back down again. And my next value is 1.3559. As you can see, I'm getting closer and closer to my value of X that I want. Okay, it's starting to repeat. So we stored, once again, write all these values down. So what I should see is X1 is 1, X2 was 1.25, X3, X4. I want you to continue to write all these X values down that we get. So if we continue through this, okay, I want to store this, store it to X, then second entry, pulls my function down. I get 1.356. As you can see, I'm starting to get closer and closer to it. Here's 33599, here's 3568. So we're getting close to repeat. Okay, and we continue this process, store to X, second entry, and now you can see I get 1.35689. I have identical numbers to this point. These are not. So when I'm getting that close, I could probably do this one more time and come up with a value. So I store to X, second entry, second entry, and I get a duplicate value. Once I get to a duplicate value, I have all that values there. I write out all the decimal places. I get my solutions. Okay, that's the value. If I would plug this value in, if I would find the value of this function, my y1 at this value, it would be very, very close to 0. So let's just do an example here. So I got vars, y vars, y1 because that's where it is, and I want to find and at my answer, what I came down to there. I get a value of 0. It's like magic. Sir Philip Isaac Newton was pretty smart. Now, let's take one more step from this. Let's make life even easier for us. In your y3, we can type in that Newton equation. We can type in x minus vars, y vars, y1 of x divided by vars, y vars function y2 of x. So now what we can do is we can call out a y3. If we take a look at our graph, what my graph look like? Oh my, I should have turned off my other functions. Oh, that's nuts. Alright, let's go my y equals, let's turn off the bottom two functions. So if I take a look at my graph, it looks like we intersect close to -1, -2, -3. If I put -3 in there, I get -27, -28. Okay, it looks like it's close to -3. So what we're able to do now is if we use an x1 is equal to -3. And if I look at my calculator, if I second quit this store -3 stored to x. Now, what I want to do is find our y3 value at this value of x. I get -3.05. Now we can store this to x, boom, and then second entry. I can pull down that y3 function, which is our Newton method, to get -3.04. Once again, we're going to get closer and closer to the value. And I want you to write out all the decimal places, because if you start at a value, I should be able to start at the same value on my calculator and be able to come down to the same values you do. So we store to x, second entry. Okay, -3.408917. Okay, so we're good through the 7s, then we have 852 and the 34. So when we're that close, we probably have one more value. We store to x, second entry, and we have a repeating value. And once again, if I would find my y1 at this, my function value at this value here, I should come down to a value of 0. Just for giggles, we'll do that. Vars, y vars, y1, parenthesis. Oopsie, I didn't store it to x. Oh, we'll see what happens. I get -2. The reason why is I pulled down one of these values up here I didn't store this to x. So I'm very close to the value of 0 at that point. This is Newton's method on how to solve the equations. I posted some solutions, or I posted some, sorry, I got tired of looking like a pumpkin. I posted some homework for you to be able to do, so some problems from the book. If you have any questions on Newton method, a lot of it turns into just basically using your calculator and the calculator exercise. So, set your calculator up. Okay, if you need to go back through, that's the nice thing about YouTube. The videos I have, you can go back over what I just did and make sure that you type in what you need to type in. Key is in your y1 is your function, your y2 is your derivative, and this could just maintain what you have there. This is not going to change from problem to problem. Okay, that's not going to change at all. So what will change is your function and your derivative each time, and then learning the process how you can store to x and find the function value at that point. That will be helpful for you. If you have questions, feel free to email me or post a comment. Maybe somebody else has the exact same question. Once again, appreciate you getting your quizzes done and to me in a timely manner. I'll get them graded and get them posted. Once again, stay safe, keep your social distancing, make sure that you keep your space, but be diligent with the homework. We have calculus we have to get through. University of Findlay is having their calculus classes still, basically in the same manner. So we will continue to have calculus and cover the material that we need to cover. Hopefully I'll be able to post more videos and do more things this week. We'll get into antiderivatives, which will be tomorrow. The antiderivatives is undoing the idea of derivatives. Once again, if you have questions, feel free to ask. Email me. At this time, I'm going to say adios. Stay safe. Enjoy the rest of your day. Adios, amigos.